Hi everyone! Today we are going to begin our discussion on waves. When we talk about waves in the ocean, you probably tend to think about surface waves and the shoaling or breaking of waves. However, there are many types of waves in the ocean, both at the surface and at depth. We will discuss many of these waves in the next few lectures, but today we're going to focus on some general property of waves and we'll start into surface waves. So today I want to give a brief introduction to waves and the equations we use to describe waves. All types of waves in the ocean or not in the ocean have some general characteristics that apply to all the waves. First, waves cannot exist on their own and require a medium to travel through. Sound waves need air to travel through. Waves in the ocean obviously need a liquid or water to travel through. Second, the medium that supports a wave must have a stable equilibrium. To understand this, picture a bowl with a marble or something in it. The marble at the bottom of the bowl is in stable equilibrium. A wave must experience a displacement or disturbing force. In this case, we can disturb equilibrium by moving the ball away from the center of the dish. The restoring force must act to return the medium back to equilibrium, and therefore it must act in the direction of the equilibrium. The restoring force is always a property of the medium, and thus each type of wave will have a different restoring force. In this case, the restoring force is gravity and points towards the center of the bowl. We know that in this case, the restoring force will overshoot the point of equilibrium and roll up on the other side of the bowl, and will end up oscillating back and forth around the equilibrium point. This ability to oscillate is a crucial property of a wave. And finally, waves carry energy, meaning that as a wave propagates, the energy required to disturb the medium from equilibrium must move along with the wave. You can think about some of these properties by thinking about a pond. Imagine this pond is perfectly calm and flat. This is stable equilibrium of the pond. A small burst of wind comes along, displacing the fluid and creating small ripples on the surface. This is called a capillary wave, and the restoring force is surface tension and the cohesive nature of water molecules at the surface of the water. Okay, so in the ocean, we break our disturbing forces into two categories. The first is surface forces, such as the wind or periodic heating like diurnal or seasonal heating. We also talk about internal disturbing forces. These can be forces such as shear or vibrations, which are responsible for sound waves, for example. As I previously mentioned, restoring forces are dependent on the medium which the wave is moving through. So each type of wave can have a different restoring force. Surface and internal gravity waves are restored by gravity. Capillary waves, as I mentioned, are restored by surface tension. Sound waves are restored by the compressibility of water. Rotational gravity and internal waves are restored by gravity and the Coriolis force. And finally, Rossby waves are restored by something called the beta effect, which again, I think from the last video or one of the previous videos, beta is simply the change in the Coriolis effect F with respect to latitude. So there are three types of waves often found in the ocean. Transverse waves are defined when particles in the medium move perpendicular to the direction that the wave moves. This is sort of the typical type of wave you might imagine. Think of two people holding both ends of a slinky, and one person abruptly gives it a vertical velocity. The wave will propagate up and down to the person standing on the other end. Longitudinal waves are defined by when particles in the medium move parallel to the direction that the wave moves. In this case, imagine your slinky again, except this time the person gives it a horizontal velocity, as to compress the slinky. This compression will propagate through the slinky towards the person holding the other end. A sound wave is a classic example of longitudinal waves. As sound moves from the speaker to the listener, each individual particle pushes on its neighboring particle so as to push it forward. Some internal ocean waves are considered longitudinal waves. And finally, we have surface waves defined by when particles of the medium undergo circular motion. Surface waves occur along the boundary of two different substances. For example, in the ocean we observe surface waves at the boundary between air and sea, as well as a boundary between two layers of water with different densities. These waves we observe at the beach or the surface of the ocean. Surface waves create an orbital path of individual water molecules at the interface as observed here. This orbital motion is observed through some depth in the water column, but exponentially decays with depth. Alright, and finally, before I get into some properties of waves, I want to just quickly mention that there are an enormous range of wave scales in the ocean. This figure is showing us wavelength and wave period, which we will talk about in a few minutes. But for now, note the range of both. For example, acoustic waves at the top of this figure can have a really, really short wave period, from about 10 to -6 to 10 to the -2 seconds. And they can have a really, really short wavelength, 1 millimeter to 10 meters. On the other hand, we have Rossby waves in the ocean, which can have wave periods from a year to a century, with wavelengths of 100 to 10 to the 7 meters. Alright, so we'll switch gears here a bit and discuss some general properties of all waves, and then dive into surface gravity waves. Here we have our displacement from the free surface. When discussing waves, we use eta to represent the instantaneous displacement from the free surface, and so eta changes with respect to time. The distance from the free surface to the crest or the trough, or the greatest difference or the greatest displacement, is the wave amplitude. The distance from crest to crest, or trough to trough, is the wave length and denoted by lambda. The wave period, denoted by capital T, is the amount of time needed for one complete cycle to pass a given point. The wave number, denoted by K, is a measure of the spatial scale or spatial frequency of a wave. It is calculated as 2 pi over the wavelength lambda and has units 1 over meters. Defined similarly, the angular frequency is a measure of angular displacement per unit time and is calculated as 2 pi over wave period t. The angular frequency has units 1 over seconds. Note here that we use sigma to represent angular frequency, but it is also often represented by lowercase omega. Once again, we also have the circular motion associated with surface waves that displaces fluid particles in an orbital path. Waves have two very important properties defining the forward propagation speed, the phase speed and the group speed. The phase speed is the propagation speed of the individual wave of constant wavelength. Mathematically, the phase speed is represented as Cp and defined as the angular frequency divided by the wave number. This simplifies to the wavelength lambda divided by the wave period t. Phase speed has units of meters per second. For individual waves, the longer the wavelength or the distance from crest to crest, the faster the forward propagation, so the larger the phase speed. The opposite is also true. Shorter wavelengths will have slower propagation. Group speed is defined similarly, except group speed is the propagation speed of a packet of waves and wave energy rather than the individual wave. Group speed is represented as Cg and defined as the change in angular frequency with respect to a change in wave number, or d sigma dk. Group speed also has units of meters per second. The difference between wave and group speed is a bit confusing. I attached a really short YouTube video that I suggest watching to help understand this concept a bit better. Wave packet dispersion occurs when you have many individual waves together, all traveling at different speeds with different wavelengths. The dispersion relation thus relates the angular frequency to the wave number. If sigma over k is constant, the wave is non-dispersive. In other words, if the phase speed is equal to the group speed, the wave packet is non-dispersive. On the other hand, if sigma over k is not constant, waves of different wavelength travel at different speeds, and waves are thus dispersive. In other words, the phase speed does not equal the group speed. The wave packet is dispersive. Now diving into our first type of wave that we'll discuss in this class, surface gravity waves. I previously mentioned this, but gravity waves are defined as a wave generated at the interface between two media of different densities, with gravity as the restoring force. This can include the air and the surface of the water, or two distinct layers in the ocean. Gravity waves, surface gravity waves, are the waves that you see at the beach, or typically think of as surface of the ocean. For surface gravity waves propagating in the x direction, we can make some assumptions to the momentum equations and arrive at our governing equations. I'm not going to write out the full equations of motion here, but hopefully we've worked with them enough at this point to know which terms I'm removing based on the assumptions. Our first assumption is that the wave movement is only two-dimensional, namely the x and z directions, so we can completely remove the momentum equation in the y direction. Our second assumption is that friction is negligible, and thus we can remove those terms from the end of our equations. We will also assume that rotation is not important, since we're looking at scenarios where Rossby number is much greater than 1, so we can remove the Coriolis term from our equations. We will also assume incompressible as always. And finally, we will linearize our remaining equations using a scaling argument. So here is our classic representation of a surface wave with depth h. We can scale our vertical velocity w to the amplitude times the angular frequency. And since the water parcels circle around the orbital path for surface gravity waves, we can also reasonably scale u to the same thing, the amplitude times the angular frequency. Now terms in the momentum equation can also be scaled. The partial derivative with respect to time can be scaled as 1 over the wave period, which can be approximated to sigma, or the angular frequency, which again is 2 pi over the wave period. Similarly, the partial with respect to x and the partial with respect to z can be scaled to 1 over the wavelength, which can be approximated as the wave number, which again is 2 pi over the wavelength. Now, under our assumptions, our momentum equation is left with our Eulerian time derivative, the advective terms in the x and z direction, and our pressure gradient term. If we substitute in, the first term can be scaled to the amplitude times the angular frequency squared. Our second term, u times du dx, is scaled to the amplitude times the angular frequency squared times Ka. The third term can be scaled in exactly the same way. Since surface gravity waves typically have a wavelength that is much larger than the amplitude, it follows a over lambda will be very small, and therefore Ka will also be small, since k is 2 pi over lambda. This allows us to neglect both advective terms, thus linearizing the equations of motion, and the resulting balance is between the Eulerian time derivative and the pressure gradient force. Our final momentum equations for surface gravity waves can be written as follows. Along with the continuity equation in the x and z direction. Now we've mentioned a few times that with our simple surface wave, we can define the instantaneous displacement as eta. We observed that the displacement follows a simple cosine curve and can be defined by the equation eta naught cosine of kx minus sigma t. This term inside the cosine function is the phase of the wave, or the position of the wave at a point in time on a wave cycle. Eta naught is the max displacement from the free surface, or the amplitude. Our solutions to the momentum equations are as follows. These are the orbital velocities of water parcels in the wave. These derivations are not necessary for the class, so I don't do them out here, but there's more information in the attached PDF below. Okay, so our dispersion relation for surface gravity waves is sigma squared is equal to gk tanh of kh, or the hyperbolic tangent of kh. So this dispersion relation can be simplified depending on if we're in shallow or deep water. So for shallow water, our kh is much less than 1 because our depth is less than our wavelength. So if we start with our dispersion relation from above, the hyperbolic tangent of kh much less than 1 can be approximated as simply kh. So substituting that into our original dispersion relation, we can replace the hyperbolic tangent with kh and get gk times kh, which is equal to k squared gh. Taking the square root, we can solve for our angular frequency and use that to solve for the phase speed, which ends up as the square root of gh. We can also use the angular frequency to solve for the group speed, which again is the partial derivative of sigma with respect to time. We end up getting that the group speed is also equal to the square root of gh. We see that in shallow water, the phase speed is equal to the group speed, and thus the waves are non-dispersive. In deep water, kh is much greater than 1, since the depth is greater than the wavelength. Again, we start with our original dispersion relation, except this time our hyperbolic tangent function of kh is much larger than 1, and will approximate to simply 1. So in this case, our dispersion relation simplifies to gk, and taking the square root of both sides gives us our angular frequency is equal to the square root of gk. Our phase speed is thus the square root of gk divided by k. And this can be simplified to the square root of g over k. The group speed can be found by taking the partial derivative of the angular frequency with respect to k, or the wave number. Doing this and simplifying gives us a group speed of 1/2 square root of g over k, or 1/2 the phase speed. Again, the group speed for deep water surface gravity waves is 1/2 the square root of g over k, which is 1/2 the phase speed. We note that the phase speed and the group speed are not the same in the case of deep water waves, and are thus dispersive. Alright guys, that's all I have for you today. As always, let me know if you have any questions, and don't forget that your midterm homework is due on Thursday, and we'll see you in class then. Thanks!